Solving general chemistry problems, reaction kinetics. A balanced overall chemical reaction equation is an important tool for tracking the mass balance in a chemical transformation. However, such an equation can be misleading if a student believes that it implies that all of the reactant molecules suddenly come together and then all of the product molecules cleanly erupt out of that tangled mess. The actual chemical dance that is hidden underneath the balanced equation consists of what are called elementary reaction steps. A sequence of such elementary steps combine together to produce the overall balanced reaction equation. But the sequence in which they appear and the relative reactivity of each one imposes some kinetic restrictions that must be considered. Elementary reaction processes are either unimolecular, involving only one reactant, or bimolecular, involving two reactants. Termolecular processes, which would involve three simultaneously, are rare if existing at all. General chemistry doesn't usually consider them. A unimolecular process could be something such as the decomposition of ozone into diatomic oxygen and an oxygen atom. Ozone is a stable molecule, and something must have happened to it to cause it to fall apart. An excitation state must always precede a unimolecular decomposition, but we seldom specify it explicitly, at least in general chemistry. The excitation step may be a collision with another molecule or even with the wall of the chamber. This collision, when represented explicitly, is usually represented by an M, nondescript collision partner. This introduces additional energy into the vibrational and rotational modes of motion of the molecule. A superscript dagger is commonly used to represent this row vibrational excitation. As the energy flows through the molecule, it can collect sufficiently in a bond that then has sufficient energy to fall apart. Excitation can also be introduced through the absorption of light, represented by h nu, which is Planck's constant times the frequency of the light, which is the product of that is its energy. This can produce row vibrational excitation, still represented by a dagger, or it can excite the electrons in the target molecule, lifting them to a higher energy level, and this is represented by an asterisk. In any case, the excited molecule can then be seen to fall apart on its own. In general chemistry, we do not discuss the excitation processes. Photochemistry, for instance, excitation by the absorption of light, is an important and extensive field of research. We instead just consider the unimolecular decomposition reaction as an elementary step that we can use in a reaction mechanism. Bimolecular elementary processes involve two reactant species and is perhaps a bit more self-explanatory. With sufficient kinetic energy and the appropriate orientation, such a reaction occurs readily and can form part of a reaction mechanism. Each elementary reaction step has a kinetic reaction rate equation written for it. In contrast to rate equations associated with a balanced reaction equation, the exponents in the rate equation of an elementary step are always equal to the coefficients of the reactant species in that elementary reaction step. Now, this is because the elementary reaction step does imply that the reaction consists of those reactants colliding with each other and the product molecules exiting from the activated complex. Remember that it is only reactants that can appear in the rate law for an elementary reaction step. Another feature of elementary reaction steps is that we consider them to be reversible. The kinetics are undoubtedly different for a forward compared to a reverse reaction, but we still are allowed to consider the reverse process. Two arrows such as this remind us that both reactions may need to be considered. However, in a reaction mechanism, we would use each reaction separately as individual elementary steps. In some instances, however, when the forward and reverse processes need to be considered, we can view them as establishing an equilibrium between its reactants and product side, and we will denote such a situation by writing the reaction equation with the double harpoon symbol, and we will write down an equilibrium equation rather than a rate equation. Now, note how we would use a capital K for an equilibrium constant and a lowercase k for a reaction rate constant. One further note about a system at equilibrium. The rate constant forward is usually not at all the same as the rate constant in reverse. You will sometimes see such an equilibrium written with the rate constants given as Kf and K sub r. In other places, these may be noted as, for instance, K1 and K minus 1. They mean the same thing. What is important, however, is to realize that the elementary reactions such as these, the equilibrium constant capital K, is equal to the ratio of the forward over the reverse rate constants. Reaction mechanisms consist of 2, 3, 4, or even more reaction steps. Now, in general chemistry, we seldom have more than 3, but in practice, there could be many more steps in a proposed reaction scheme. The sum of all the elementary reaction steps, now think here of Hess's law, produces the overall balanced chemical reaction equation. Now, some scaling and adjusting may be necessary. But this is one of the key requirements when developing a reaction mechanism for some process. It must reproduce the process. As an example, here's the reaction between an iodide ion and the hypochlorite ion. 3 sequential steps are proposed. The first and third are at equilibrium. Note how, when we sum the 3 equations, while canceling redundant species on each side of the equation, as in Hess's law, we obtain the overall balanced equation. When several steps are involved, it is common that some chemical species is produced in an early step, and then that same species is consumed in some subsequent step in the mechanism. It does not appear in the final balanced reaction equation, but it appears and then disappears as an essential part of the overall mechanism. Such a molecular species is called a reactive intermediate. And an intermediate leads a brief life and is soon consumed and leaves no evidence of having been there. Modern kinetic research, however, often attempts to observe or even trap reaction intermediates. If one is able to prove the existence of such an intermediate, it is strong evidence that supports one proposed reaction mechanism over another. In general chemistry, you will be asked to be able to identify reaction intermediates. You will recognize them by their appearing in one elementary reaction and then disappearing in a later one. When you go to a bank to apply for a loan, you might fill out an application, which then has to work its way through a series of different individuals in order to process your application. The first one may enter it into the system. They are pretty fast, entering 60 per hour. Another may evaluate the merits of your request. They have more work to do, and perhaps they are more disorganized, and they can only process 5 per hour. Then it might be passed on to another who will prepare the paperwork to approve your loan and initiate the transfer of funds into your account. They can handle 40 per hour. If you are waiting around to hear the outcome of your application, clearly crossing the second desk is the one that will determine how quickly you are informed. Step 2 is the rate limiting step. It is common in the analysis of reaction kinetics to find that one step in the elementary reaction that is substantially slower than the others. This may be because it has a larger activation energy, or perhaps it has some significant orientation restrictions, but whatever the cause, its slower reaction rate means that it tends to control the overall reaction kinetics. Commonly, we use the rate law for this elementary step to guide our analysis for the overall reaction process. This analysis, which is the central goal for this presentation, will lead to the conclusion that the proposed reaction mechanism produces a rate law that is consistent with the rate law that is measured experimentally. The reaction mechanism explains the observed rate law. This is the fundamental purpose of developing a reaction mechanism, to explain the observed rate law. Consider the reaction between nitrogen dioxide and carbon monoxide. Nitric oxide and carbon dioxide are the products. Experimentally, we find that the rate law is second order in nitrogen dioxide. The following reaction mechanism is proposed to explain this observed rate. 2 NO2s react to form NO3 and NO, and then NO3 plus CO goes to NO2 and CO2. If you add these 2 equations together, you do get the original balanced equation. The first elementary step produces a rate law that is consistent with the observed rate law. We can conclude, perhaps, that the first reaction step is very slow compared to the second step, and that is why it dominates the reaction kinetics for the process. Here's another example, the reaction of nitric oxide with oxygen. 2 nitric oxide molecules pick up an oxygen atom to make nitrogen dioxide. The observed rate law does indeed mimic the stoichiometry of the balanced reaction equation. Does that mean that we should expect a termolecular elementary reaction? We've already indicated that such a process is rare if ever found. Is there another way to achieve the same outcome? Now look at this proposed reaction mechanism. What if the first step was for 2 NO molecules to react and find themselves in equilibrium with a transient intermediate, the very reactive molecule N2O2? Then this intermediate species could react with the oxygen to produce the desired products. This last step has a rate law that is different from that observed. In fact, it contains within it the concentration of this reactive intermediate. We cannot measure its concentration, so we can't use it in a rate law. Whenever we develop a rate law from a proposed mechanism, we cannot use the intermediates in the expression. So how could we get rid of the intermediate, and what would we replace it with? Go back to equation 1. Since it is in equilibrium, we will write out an equilibrium expression for it. When you look at this equation, you can see that it is rewritten to solve for the concentration, can be rewritten to solve for the concentration of N2O2. With this, we can replace the N2O2 concentration in the second equation's rate law to obtain this expression, which is consistent with the observed rate law. Some important points to remember when taking a proposed reaction mechanism and deriving an overall rate law from it. First, the slow reaction step governs the overall kinetics. Its rate law leads to the observed rate law. Second, any elementary reaction steps following a slow reaction step can be ignored from the standpoint of kinetics. They do not influence the reaction kinetics, for as soon as the slow step produces some products, they quickly react to complete the process. Third, if the slow step rate equation involves an intermediate, this must be removed by using the rate laws or equilibria of previous reaction steps to cancel it out, and have only well-defined species, those that appear in the overall balanced expression, in the final rate equation. Fourth, an elementary step that is identified as being at equilibrium is characterized by an equilibrium expression, which is the two rate expressions, the forward and the reverse rates, combined. This is commonly used to cancel intermediates in a subsequent rate expression. And finally, you may see authors combine a collection of unspecified constants to form a single renamed constant. There's nothing wrong with this. You may sometimes see an expression with constants from several elementary steps, and other times you may see just a single constant that is the product of the others. Both approaches are acceptable. Identifying a rate-determining step is one approach to interpreting a reaction mechanism. It is commonly taught in general chemistry courses. Another procedure is available which does not rely upon knowledge of the relative rates of the elementary steps. You do not need to assume, at least at the outset, which reaction is slow and which ones are fast. Now, it is known as the steady state approximation. It leads to expressions for the reaction rate that are usually more complicated than when the rate-limiting step approach is used, but we are able to proceed without claiming we know something about the relative speeds of the different reaction steps. Look again at the nitric oxide-oxygen reaction we were just examining. Consider this three-step reaction mechanism. We do not need to assert that the intermediate N2O2 is in equilibrium with the reactants, and we do not need to claim to know that the third step is the slow step. To proceed, choose one of the three elementary steps to start with. We'll look for one that might be closest to represent the reaction equation. Let's start with 3, since it includes the disappearance of oxygen. The rate law from 3 involves the product of the N2O2 and the O2. We still need to eliminate the N2O2. How to proceed? We know that N2O2 is a very reactive intermediate species. Its concentration, whatever it is not going to be very great. Its production and consumption will proceed until it reaches some balance. We can anticipate that its small but non-zero concentration will remain constant throughout the bulk of the reaction. We assume that the N2O2 concentration achieves a steady state concentration. This is the assumption made in this approximation. For intermediate species, this is commonly seen to be a good assumption. So what mathematical construct would we use to describe this situation? Well, the time derivative of the N2O2 concentration expresses how the concentration changes with time. But we are asserting that it does not change, that it is in a steady state condition. Therefore, our approximation is that this derivative equals 0. This means that the rate at which N2O2 is produced minus the rate at which it is consumed must equal 0. Or in other words, the rate of production must equal the rate of consumption. So what is the rate of production of N2O2? Which means, in which equations does it appear as a product molecule? Well, it's only produced in step 1, so the rate law for that equation must be the rate of production of N2O2. On the other hand, where is it consumed, or where does it appear as a reactant? Both in steps 2 and 3. Here's the expression for its consumption. Now, the point of this whole approximation is that these two expressions must equal each other in order for the concentration of N2O2 to reach a steady state. Now, here's that expression again. We need to solve it for the concentration of N2O2 because that is the value we are trying to replace in the rate expression since it is an intermediate. We can factor out that concentration, move the residue to the denominator on the other side. Here's the expression for the N2O2 concentration. We now substitute this back into the expression we had for the rate of step 3. Gather the terms together, and our final expression for the rate of the reaction is this. Now, clearly this is more complex than we are used to seeing, but it's perfectly valid and has been arrived at with fewer assumptions. Now, what do we make of the observed rate law, which is this? How do we reconcile these two expressions? Clearly the denominator is the difficulty. So what if K2 was much larger than K3 times O2? Now this inequality would still hold even if we multiply both sides by N2O2. But these expressions are now just the reaction rate for the elementary steps 2 and 3. The proposed inequality is essentially saying that step 3 is slow and step 2 is fast. So what would happen? Well, if K2 is very much larger than K3 times O2, then adding K3 times O2 to it will not change it very much. We conclude that K2 plus K3O2 is essentially just K2. Substitute the approximation in the denominator, the K3O2 term then disappears, and we obtain some constant times NO2 squared times O2, which is identical to the expression we find by using the rate-limiting step approach. The difference is that we did not need to know beforehand that step 3 was the slow step. Instead, by invoking the very reasonable steady-state approximation, we found that step 3 must be the slow step in order to agree with the experimentally observed rate. Here is another example, and you will not likely encounter this one this challenging again in general chemistry. Derive a rate law for the decomposition of dinitrogen pentoxide. Here is the balanced reaction equation. Assume the following four-step reaction mechanism. Inspect the elementary reaction steps carefully, and you will note that both NO3 and NO are reaction intermediates. They are formed in one step and then consumed in a later step. Apply the steady-state approximation to both species. First, NO. NO is produced in step 3 and consumed in step 4. We add the rate from step 3 and subtract the rate from step 4, write out the rate laws, and equate them. Solve for NO. Note how the NO3 cancels out, and we are left with just the ratio of two rate constants. Now, what about the nitrogen trioxide? Well, there's a little more algebra with NO3. It is formed in step 1, but it's consumed in steps 2, 3, and 4. Write it out, equate to 0. Equate the consumption processes with the production process. Substitute for NO, gather the two terms in just NO3 together, factor out the NO3, now solve for NO3. Now pick the most convenient step to define the rate law. Step 3 looks promising as it includes the production of oxygen. That's a rather complex looking thing, isn't it? Since the coefficient for oxygen is 1 in the overall balanced equation, the way we wrote it, then this would be the rate of the reaction. However, the measured rate law is just a constant times the N2O5 concentration, so we again look at the denominator. If we say that K2NO2 is very much less than 2K3, then we could cancel some things out. Multiply both sides by NO3, and you can see that this statement is equivalent to saying that 2 times the rate of step 3 is much greater than the rate of step 2. We therefore assume step 2 to be slow and step 3 to be fast. Then the denominator is essentially just 2K3. Substitute, cancel, and you see that we now have the same form as is measured experimentally for the rate law. With this proposed reaction mechanism and attempting to force it to produce a rate law that is consistent with that which is observed experimentally, we find that we are required to draw some conclusions about the relative rates of some of the proposed reaction steps.